Hello, this video is going to be the sequel to this previous video I made. If you're trying to make a moral agent, you need to use an agent. So go back, watch this video first, then come back to this video now. This video is going to be about if you manage to make an AI, use the moral system described in that video, but you don't tell it what its moral weights should be. You just tell it that its moral weights should be such that it makes these decisions and some list of decisions that are where you know what the right decision is and what the wrong decision is. Like, for example, if you uh, tell the AI, hey, this is your moral system, but I won't tell you the moral weights, but what I will tell you is that if you had to choose between making four happy cats or four happy dogs, you should choose to make four happy dogs. You should donate to a charity that helps four happy dogs live longer than donating to a charity that helps four happy cats live longer, for example. That if you gave it some list of decisions like that and you gave it the right moral system, then on average, does it make fairly good decisions, at least at first? Um, that's essentially what this video is going to be about. Um, and it's sort of a proxy for the question, um, if we give an AI this moral system described in this video, then will it be okay at first? Will it not kill all of us immediately? Which is really the main concern. Um, and this video doesn't really answer that question, which is way more important, which is will it kill all of us instantly if we give it this moral system? This one, this video answers a loosely related, much more complicated math question. This video is mostly going to be a lot of math. Um, so, as a bit of a preview for what our loose proxy question is going to be, um, let's move over here to talk about some math. So, as described in the previous video, the AI that we're designing has this moral system. That is some model of the world. This is the world. It's different things in them. Happy dogs, happy bunnies, cats, sleepy people, happy people, people going through depression, divorces, poverty, uh, birth, um, animals going through all the things animals go through, chickens in factory farms, um, insects looking for food, all of that stuff, and it assigns some moral value to that state of the world, or to different things in that state of the world. Like maybe it assigns a value of 4 to each happy person, a value of 1.5 to each happy bunny, a value of 2 to each dog, and so on and so on. Or really, it assigns value to conscious experiences that are good, and it has some correlation between the physical world and conscious experiences that are good, that it learns based on um, animals' decisions, as described in the previous video. Um, but at first, it's going, like, in the first 10 seconds, it's not really, well, no, it's going to learn a lot of information in the first 10 seconds of its existence. But in the next 10 seconds of its existence, it's not going to learn that much information. So, anyways, some model of the world like this. And it makes decisions like this. It has some model of the world if it makes one decision, of what the world would look like if it chooses option A, and some model of the world if it chooses option B. So it's choosing between this world with 2 dogs and 4 cats and this world with 3 dogs and 1 cat. And let's say it values dogs at a value of 2 and cats at a value of 1. Um, Now this calculation is the same as doing the number of dogs in scenario A, which is 2, times the value of dogs, which is 2, plus the number of cats in scenario A, which is 4, times the value of cats, which is 1, versus that same calculation for scenario B, or sorry, option B. Or no, this is option 1, this is option 2. 1, 2. Now this, as we're about to see, is the same as this calculation. Now what does this mean? Luckily, we have this brilliant video by 3 Blue 1 Brown that explains it for us. Um, Dot products and duality. Um, all right, so that's the explanation of that. Um, and visually, this kind of looks like this. Which is bigger, the dot product between this thing and our moral weights vector of 2, 1, or this thing and our moral weights vector of 2, 1. And doing this projection thing, first we map this onto the black vector, and then we scale it up by the weight of the black vector. Um, and then we do that for option 1, the pink one, and we see which one is bigger. Now, one thing to note here is whether we decide whether we decide option 1 or option 2, or sorry, whether our AI decides option 1 or option 2, doesn't depend on the um, scale of this vector. You know, if you double the scale, then the dot product between this, our moral weights vector, and option 2 is going to double, and the dot product between our moral weights vector and option 1 is going to double. So, you know, if option 1, if option 1's vector is larger than option 2's vector, then it's going to stay larger if we double the size of both, or if we multiply the size of both by 0.5 or 0.2, um, or so on and so on. Essentially, it doesn't matter if our AI values everything twice as much, or 3 times as much, or half as much, because it'll make the same decisions either way. Um, it does matter if our AI cares about everything 0 times as much. In other words, if our AI doesn't care about anything and goes insane and cares about everything equally, um, that would be terrible. Um, and it would also matter if our AI cared about everything -1 times as much. Um, because that means like everything good it thinks is now bad, and everything really good it thinks is now really bad. Um, this is an unacceptable risk. This would mean our AI actively tries to make the world as bad as possible. And the only difference between an AI that makes the world as good as possible using all these assumptions, and a world where our AI trying to make the world as bad as possible under all these assumptions, is just a single character, a -1. So whoever's writing the code for this would need to be extraordinarily careful, more careful than humanity has ever been in any scientific experiment. Um, And that's maybe an unacceptable risk, and maybe you should use a better system with more checks or something. You know, um, obviously for all AIs, what you should always first sandbox the AI and test out what it does in different situations. That's just a given as like a minimum check. Um, and also you should hopefully be able to prove that the AI you make is aligned. That's a field of study is figuring out how to prove if an AI is aligned. But I'm going off topic. This is supposed to be more about math. Um, so we're still setting up what our question is going to be. And to help us set up that question, we have some more math, which I'm just going to drag over. Um, so let's say we, as mentioned earlier, we're not going to give our AI explicit moral weights. We're not going to say dogs are worth two, cats are worth one. Um, so we don't know what that is. Um, so let's represent it with this. And let's ask ourselves, like, we don't know what this vector is now. And let's ask ourselves, um, oh, and let's say we told our AI that in this decision between two dogs and four cats or three dogs and one cat, um, that let's say we told it option one is better. What does that tell us about the set of possible moral weights that would lead to that decision? Because remember, our question involves that. Well, first let's ask ourselves, what's the set of moral weights vectors here where um, it doesn't matter where it thinks both options are equal? Well, the value of the first option, as previously stated, is the dot product between the option one and our moral weights vector. And the value of option two is the dot product between option two and our moral weights vector. And let's say they're equal. Then some simple algebraic manipulation. The first world minus the second world times our moral weights vector has to be equal to 0. Now, what is this vector going to look like? Well, first we have our option 1 vector, and then we subtract option 2. So we do option 1 minus option 2 gets us this vector in red. So the dot product between our moral weights vector and this vector in red, when that dot product is equal to 0, both options are equally valuable. And as mentioned in the video, the dot product is 0 when it's perpendicular. So going back here, this is the line where it's 0. Above this line, it's positive. So above this line, we would choose option 1. And below this line, it's negative. So we would choose option 2. Now let's say, so so now we know that our moral weights vector is going to be in this section. We don't know what it is yet. We just know that it's going to be in this section. And let's say we gave our AI a bit more data. Let's say we gave it these two choices. That's option 1, and this is option 2. And let's say we told our AI that option 2 is better. That means we subtract option 1, and now let's get our complicated number thing. So now we can just clear this up. Basically, we're doing the exact same process as we did for the first decision, but now for this new decision. So now we know that, you know, the dot product between our moral weights vector and this vector here has to be positive. So this vector has to be, our moral weights vector has to be in this range. It has to be on the left side of this line here. So it has to be in this range, and it also has to be in this range. So in other words, it has to be in this range here. And we can keep doing this And let's say we found out from another decision that RAI has to also be in this range, and then another piece of decision data tells us that RAI has to be in this range. And the more decisions we give it, the narrower and narrower this range gets, which is what we want. We tell our AI a longer and longer list of good decisions. Um, its moral weights should be more and more accurate. But how much more accurate? And that is going to be the math question. More specifically, let's say there are um, n, or let me double check this. Ignore this. This is just a math thing for me. Yeah, n as in like um n as in next, that kind of n. Let's say there are n different things we care about instead of just two, cats and dogs. You know, and if it's three, might be cats, dogs, and bunnies, or four cats, dogs, bunnies, people, five cats, dogs, bunnies, happy people, sad people. Now, in the real world, n is going to be infinity. There's going to be an infinite amount of different things we care about. First of all, there's going to be slightly happy people and slightly more happy people. Second of all, there's going to be cows, pigs, chickens, um, New World screwworms, um, E. coli, all that stuff. But anyways, n different things we care about, and let's say we feed our AI m, as in monster, m different decisions. Here we have um, one, two, three, four different decisions where we say this is the right decision. And for each of those decisions, let's say um, well, we give it for sample decisions where we highlight the correct option. And for each of those decisions, let's say there's only two options, and for each of those two options, the number of expected dogs will follow a Gaussian distribution with a mean of 0 and a variance of 1. The number of cats will also be a Gaussian distribution with a mean of 0 and a variance of 1. Same with the number of bunnies, people, etc. for each of the n things we care about. This whole vector follows a Gaussian distribution along in the set of all possible worlds. Um, and these two vectors, let's say they have no correlation. This is a very specific distribution and does not at all reflect the real world. Realistically, we're going to be choosing decisions where, you know, actually, we might, this model is pretty strange. We're probably not going to give our, it would be weird if we managed to give our AI a sample of decisions like in the Korean War. Should you have sent in more troops or less troops? And like we somehow know exactly what world that would result in an expected value. That seems weird. This whole thing is kind of detached from reality. But anyways, um, if you're continuing to follow the question, let's say we gave it that set of decisions, and that will give us some set of possible values that our moral weights vector could be in. In this case, n is 2, and sorry, m. I meant to say m. There are m things no, yeah, there are m things we care about. M as in monster. There are m things we care about. In this case, m is 2. And we give it n decisions. N is in next. In this case, n is 4. Um, in that scenario, this is the set of possible moral weights vectors. And let's also, and this is still the question, mind you. Let's say, and let's also assume, as part of our question, that our moral weights vector has a length of 1. Because as mentioned, the scale of this vector does not matter. If our AI cared about everything twice as much, it wouldn't matter. Half as much, it wouldn't matter. 0 would be disastrous. -1, it would be insanely disastrous. Um, but here the scale doesn't matter. So we're assuming the scale is 1, not 0 or -1. Um, Assuming that, let's say we gave our AI a decision between um, O different options. O is some number, and each of those options follow that same distribution on the things we care about. A Gaussian, like the number of dogs for option 1 of this hypothetical decision we're making, our AI is making. The number of dogs will follow a Gaussian distribution with mean 0, variance 1. Same with the number of cats, number of chickens, bunnies, etc. For all of the things we care about. And that's true for all of the O options we're given. Um, and each of these each of these O vector options are completely independent. They follow independent Gaussian distributions. Given this, let's say our AI randomly chose a starting vector out of the set of possible valid starting vectors. Not just, like, it could choose this one and it's equally likely to randomly choose this one. Side note, what would be better is if it averaged across all possibilities of moral weights vectors weighted by the probability that those moral weights are the true moral weights. Um, that's what it should do. That's what we would want to program, but the math for that is way harder. When M, as in monster, is larger than 2. It's way harder. But that's what we should do. That is what we should do if we're going through with this. Um, but let's say it was random. This is equally likely to this. Um, and what I mean by random is like, because it's the set of possibilities is going to be on some circle or sphere or whatever, because length of 1. Um, any place with the probability that our moral weights vector on that circle or sphere or hypersphere or whatever is in some certain section of that circle, sphere, hypersphere, or whatever, is equal to the volume of that part of the circle's sphere, whatever. So, like, the probability that it's on this half is going to be 1/2. The probability that it's going to be on this half is going to be 1/2. Well, the volume of that part of the circle divided by the total volume of the circle. Basically, it's going to follow an even distribution where any area is equal to any other area. Now that all the assumptions are out of the way, we can finally ask the question, what is the expected value of the world that it chooses um, the expected value of the world that it chooses given its moral weights vector, given all those assumptions, the expected value of that using the true moral weights. Not the ones that it chooses, but the true moral weights. Um, and another assumption to get out of the way is let's assume that the true moral weights lead to all of these decisions. So, like, if we knew what the true moral weights were, let's say this exactly was the true moral weights of the world, and it made that would lead to all of these red lines here. Um, in the real world, we don't know what the true moral weights of everything is, but all right, so that's the key question. And here is the math for it. Or no, first I should do a quick recap of the question. So there's M as in monster, things we care about. We give it N as in next, um, sample decisions, where for each of those decisions, there's 2 options, and we tell it what the right option is. Each of those options, the number of dogs or cats or chickens or whatever, follows some Gaussian distribution with a mean of 0 and a variance of 1, so the number of dogs in option 1 of sample decision 1. Um, follows a Gaussian distribution with mean 0, variance 1. Um, so we give it that there's some set of possible moral weights vectors that could be correct. We assume that the weight of that vector is 1. Our AI randomly chooses one of those vectors following a normal distribution out of a set of all possible vectors then. And then it gets faced with a decision between new vector new worlds that follow that same Gaussian type distribution. An expected, and it will choose one of them. An expected value, what is the value of that option given all of those assumptions and given our true moral values, moral weights. All of this is a proxy for the first decision that our AI will make with all of these assumptions. How good will it be? Or at least will it be okay? And now on to the math. Well, the first thing I'm going to explain is better explained here. So we're going back to this zone. Um, the first thing to note, or actually no, this is better explained in this zone. Um, how do I... Give me a second, I'm just rearranging some things. Okay. What you're looking at now is um, a GeoGebra file version of everything I just showed you. Um, and right now I'm just rearranging some things in that GeoGebra file. So feel free to ignore. This used to represent option 2. Let's say that for now this represents what or actually no. Um, we're leaving that alone. What we're going to get at now is we're going to pull that out. Where's the, here we go. And then there's also a vector for that we're going to pull out. Here we go. We're going to move this. Um, hmm, what is it that huh? Hold on, I gotta figure out what vector I'm missing. Or including that I shouldn't be including. Is that, is that vector meant to be there? Is that vector a bug? Hmm. Almost there. That's what A1 is going to represent later. Um, okay, so let's say our true moral weights, and we're looking at the scenario where M, as in monster, is 3. We care about 3 things: the number of cats, the number of dogs, and the number of bunnies. And let's say the true moral weights of the world is that we only care about bunnies with a value of 1, and we care about everything else as 0. We're going to run with this assumption the whole time, um, because as I'm about to explain, this whole setup is rotationally symmetric. It does not matter what the what our true moral weights vector is. The calculation is the same. Um, and this point here, A1, let's say that's our AI's moral weights, the one that it randomly chooses. Um, and this is the set of possible points it could choose. See, it's on a sphere because, see, remember, the set of possible points it could choose from has a length of 1. Um, see, it's all coming together. Um, and let's say this vector um, is this. It doesn't care about cats at all. It cares about bunnies as 0.5 and dogs as the square root of 0.75. That has a weight of 1. Um, what I'm going to explain is that the expected moral value of a decision under this circumstance is equal to the expected value of the decision, assuming the moral weights of A1 are correct, times the dot product between A1 and the true moral weights. Or actually, no, you know what? I'm going to switch it. Let's say A1 is our true moral weights, and this other thing is going to be our other moral weights. Um, and then let's bring back the thing for option 2. Um, let's bring back the point for option 2. No, that's a segment. Oh, well, no, I do want that segment. Is that the right point? Is that the right point? No, it's probably up here. Oh, here we go. Oh, those are the wrong vectors. Okay. I'll just, oh, wrong line. I want to increase the thickness of this vector here, but I don't think I'll be able to. Oh, I guess I will be able to. What do you know? All right. So we have here the option that, let's rename this option, or let's rename this best option. So this is the best option under these moral weights. Um, and this is the dot product between the best option and our moral weights. Um, see how it follows this line here, this projection line? That projection math also works in 3 dimensions. If you want to know why all of this works, watch this video by 3 Blue 1 Brown. Now, as explained in this other video by 3 Blue 1 Brown, hold on, I'll just find it on his channel. Um, go watch this video if you want to not be to have an explanation for what I'm about to say. Where is it? It's in his Y pi section. Yeah, Y pi. Oh, I guess not. then it must be in his, um, it must be in his Gaussian distribution playlist. Yeah, here we go. Well, Gaussian distribution, normal distribution. Sorry, this is just an ad. Okay, so watch this video first if you want to understand what I'm about to say. Um, or if you want to know the proof of what I'm about to say. You'll understand it either way. If you want to know why what I'm about to say is true, watch that video. If you are okay just knowing that it's true and not knowing why, you don't have to watch the video. This is what the video is called. Feel free to watch it. Um, the distribution of um, this vector here, if we assume that like there's only one option, um, if we assume that O is one, um, the distribution of the dot product between this vector and this unit vector is a normal distribution with mean 0 and variance 1. Because like um all of this whole distribution is rotationally symmetric. Because remember, I'll set this back here. Um, the distribution of some options number of dogs is a mean with a is a normal distribution with a mean of 0 and a variance 1. It looks like this. Same with the number of cats. Um, and this whole and the whole distribution of the whole setup would be the same if we just rotated the axes. Um, if the distribution for the number of dogs and the number of cats is the same as the distribution of the best option along this line or this line. If we rotated the whole setup, the distribution would look the same. That's one statement. The proof of that is in that video, y is pi the normal distribution. Um, Same thing goes in 3 dimensions if we rotate things in 3 dimensions. So if we just rotate number of dogs to be that vector, then this will follow a normal distribution. Um, so that this whole setup is made to be rotationally symmetric. That's why I used the Gaussian distribution for so much of this, is to make it all rotationally symmetric. So given that this, the distribution of one thing, the dot product between one option and this vector follows a Gaussian distribution, the thing for um, the distribution for another thing will also be a Gaussian distribution. And I'm all right. So train of thought. Now that that's out of the way, I can better explain why the expected value of this decision, where our moral weights are 0.5 for bunnies, 0. Square root of 0.75 for dogs, is going to be the expected value of the decision, assuming those moral weights, times the dot product between that and the number of bunnies. So, first thing first, can I get to this point, or is it too small? Or, hold on, let me find the point. No, I'll have an explanation in like just a second. Um, I just need to find the points. So HB, do I have, okay, so H is now highlighted. Now what I can do is do the segment between this. Wait, no. Hmm, which would it be? Parallel line, perpendicular line. Figuring out how to construct something. Yeah, I think we'll need to do. Just ignore this as just some GeoGebra setting up stuff, is all. Here we go. Particular line. How do I set this up? Hmm. Perpendicular plane, maybe? Parallel plane. Intersection between this and that. All right, it's all coming together. Okay, so this point here, um, oh, wait, no, yeah, this is, oh, okay, here we go. Things are coming together. So, V1 is the true value of the option we end up choosing, the best option. Um, and you'll see the dot product between the best option and our true moral weights vector here. Um, the dot product between this vector and this vector is um, the same as the dot product between this vector and this vector, which is this vector, times the dot product between that vector and this vector, because they're on the same plane and they lead to the same point. Uh, if we move this plane around, you'll see that, like the, oh, wait, no, I'm wrong. I thought I was onto something. Disregard what I just said. Um, well, instead, what we're going to explain is something much more simple, which is if the expected dot product between our best option and what we think is the right decision is like 2, or no, is like 4, um, then our distribution will go around 4, which means our just, so let's settings show trace. So that right here has an average of 4. And that if we trace that on the way um, the way 3 blue and brown did in the previous video on dot products to this vector, it would all of the stuff clumped around 4 would be stuff clumped around 2. Okay, so that's why an average of 4 times a dot product of 1/2 leads to an average of 2. That's why that previous statement is correct. So, now our full question from earlier is split up into 2 easier questions. What is the um, what is the expected value of the best option O given our randomly chosen moral weights times what is, and the answer to that question is some number. That number times the the number from this other question. That question is what is the expected value of the dot product between this vector, um, uh, ignore all that movement, this vector here, and our true moral weights, that is some number. Those two numbers multiplied together is the answer to our original question. Now, what is the formula for the first question? For the number in the first question? Well, first thing to remember is that our best option follows a Gaussian distribution. Sorry, each option, the dot product between each option from the set of O options and what our AI ends up choosing as its moral weights vector is going to be a Gaussian distribution with a mean of 0 and a variance of 1. Um, so we have O different number. So this is the real question for the first thing. If we have a Gaussian distribution, sorry, if we have O different Gaussian distributions with a mean of 0 and a variance of 1 that generate O different numbers, and we choose the best one, what is the expected value of that best one? Now, the math for this is pretty simple, but it would take a while for me to explain. If you want, you could just copy paste that question into like any AI these days. You could just ask ChatGPT that question. It'll explain it pretty well. It's just some basic calculus, but I'll skip over it here. If you're curious, though, ask like ChatGPT or something. It'll give a pretty simple answer. So now we can get into the real juicy math question with a lot of fun diagrams. What is the expected dot product between this vector and this vector? And I'm not switching their meaning, sorry, and I'll just switch their place in their meanings now, because now using the black one is gonna work better. So, um, I'm just switching which one we're using as, like, this black one now represents the true moral weights of the world. This one now represents what we think the correct moral weights are. I'm just gonna turn off this point. Um, Now, first thing I'm going to explain for this question is what does, and I'm now going to rename this from best option back to option 2. Um, and I'll set this up. Um, and I'm going to need to bring back some vectors from a second ago. So, option 2, just how we got those red lines from in the 2D case, we can get red lines or things like red lines in the 3D case. Um, just instead of red lines, we get red planes. Um, or hold on, let me get the vectors to explain this real quick. Let me get all of the vectors and all of the points. Where'd my pink vector go? And where's the point for the pink vector? Okay, so let's make a relatively simple case here. Let's say option 1 is 2, 2, 2. So let's get it to that. 2, 2, 2. Is that right? 2, 2. Um, Oh, I could just type it in here. 2, 2, 2. And let's say option 1 is going to be 2, 2, 0. Now I'm gonna switch which one's gonna be 0 and which one's gonna be 2. 2, 0, 2. How's that? There we go. Yep. So, um, we do the same math as before, the same subtraction thing. And if we look at it parallel, you can kind of see it. We do option 2 minus option 1. Um, let's just recolor this to keep it consistent. Um, pretend that's pink. To get this vector, the dot product between RAI's morals and this red vector here has to be positive, which means that um, R point or RAI's moral weights have to be past this red line, but instead of a red line, it's a red plane. Hold on, let me perpendicular line. I'm looking for a perpendicular plane to this vector. Yep. And then I'll color this thing red. Our point has to be on this side of this plane. It cannot be on this side of this plane. Otherwise, it would choose option 1. If it's on this side of this plane, it chooses option 2. If it's on this side of this plane, it chooses option 1. Um, and now what we can do is I can show you um, here we go. Now we have a surface that exactly shows what this is going to look like. Now, one thing to note is this red line also follows that same Gaussian distribution everywhere thing because it's um, value for each, like the number of dogs. Like, let's say we randomly generated a new value for this red vector here. The distribution for the number of dogs in that vector is going to be equal to the distribution of the number of dogs in option 2 minus the distribution of dogs in option 1. Um, in other words, it's going to be a Gaussian minus a Gaussian, which is a Gaussian. That's also explained in another 3 blue 1 brown video, why Gaussian plus a Gaussian equals a Gaussian. Or a normal distribution plus a normal distribution makes a normal distribution, and a normal distribution minus a normal distribution is the same thing as a normal distribution plus a normal distribution times -1. And because a normal distribution is symmetric, it's equally likely to be -1 as it is to be 1. It's the same thing as doing a normal distribution plus a normal distribution. Basically, we're doing one vector that can be anywhere where its radius, its distance from the circle, follows the Gaussian distribution, and um, where it is on the circle, um, like its angle, follows um, a uniform distribution. Um, it's equally likely to be 10 degrees for, from this vector as it is, or like it's equally likely to be on in this semisphere as it is to be in this hemisphere, or in this hemisphere, or that hemisphere, um, or this hemisphere or that hemisphere. Anyways, point being, um, with a bit of simple math, it's pretty easy to see that um, This vector here, if we generate like 10 of those vectors, the distribution for each of those vectors also follows that same kind of Gaussian distribution thing, just with a variance of the square root of -2, meaning it's also rotationally symmetric. So, let's strip off everything that we have here, or everything that we no longer need here, um, and just get the things we need for what I'm about to show you. Oh, but one thing to note is obviously our red vector has to be in this upper hemisphere. Um, it has to be in this hemisphere here. It, um, why is that? That is because this is the hemisphere where the dot product between, or rather, this point scaled down such that the scale of this vector is 1 has to be in this hemisphere, whatever the red line is. Um, and um, the reason for that is because every, the point, the dot product between the red vector and the black vector has to be positive. If it's below this hemisphere, it's going to be negative. If it's exactly on the dividing line, it's going to be 0. Here, it's going to be positive. It's never going to be on the dividing line exactly because the probability of that is not non-zero. So it's going to be on this hemisphere. So now that we got that out of the way, now we can clear everything up and add all of the things we need to add. And we can get rid of option 2 and option 1. And now I just have to figure out points I need to add back. We can get rid of that perpendicular plane. Um, this is just some basic setup stuff. Back some points and remove some points. What's this vector doing here? Is that the... I'm gonna get rid of that vector. It's bothering me. It's not supposed to be there. If only I can figure out which of these it is. What? It's not that one. It's not that one. It's not that one. This vector should not be there. What is going on? Okay. And now let's get... There we go. Okay. So remember, this black circle here, this one, everything above that, the dot product and our true moral values is positive. Everything on this plane, it's 0. Everything below this plane, it's negative. That's what that means. Um, Now we're adding some vectors. No, I guess they'll be... I guess I used segments instead of vectors here. I'm gonna bring in the points first. This is just ignore this part. I'm just figuring out what points I need to add for this visual. Is that correct? No. Is that correct? Do I move around? No, I don't. Is it O? No, I gotta figure out where the points are that I'm moving around. Okay, here we go. So now I have one of them. Okay. So R is okay. So this purple thing now represents one of these red vectors from earlier, and this hemisphere represents one of these red lines from earlier. We have two of them, one for some decision that we've color coded purple, one for some decision that we've color coded blue. I'm just getting the stuff in for blue to work. Is this it? Yeah, here we go. So U and um, U and Q are two decision things. Both of them have to be over this black line. Both of them are on that unit circle. This intersection between the hemisphere of the blue one and the purple one is the set of possible moral weights that we could end up with. So, like, let's do a sample of some scenarios just to give you a sense of what could happen. Let's say we randomly generate that Q and we randomly generate this U. Oh, and the point of all that math from earlier is that U and Q follow a uniform distribution, but they're somewhere on this hemisphere. This one. As in, like, their number of bunnies is not negative. Um, and A is going to be some point that is on both of these hemispheres. A can have a negative number of bunnies. It's just unlikely. Um, so like A could be over here. And A is randomly generated in between these two hemispheres, on the intersection of these two hemispheres. Um, A cannot be over here. A cannot be down here. A has to be in here. Our question is, what is the expected value of the dot product between A and the number of bunnies? Um, so, what is that? Well, um, the thing we are going to see, well, no, first things first. The expected dot product between this point and this point, the expected value of that is going to be equal to, um, for every point on the unit sphere, we calculate the dot product between that point on the unit sphere and our true moral weights vector times the probability that that point will be chosen. And the probability that that point will be chosen is going to be equal to um, the um, probability that that point is in the set of possible points. Um, if we generate some random U and Q, Um, so like here, A doesn't end up in U. Here, A does end up in U. Um, times the probability A ends up in Q. So that's the probability. So the probability A is in all of the allowed hemispheres. So the probability that it's a possibility divided by the probability that it will, sorry, times the probability that it will get chosen given the fact that it's possible. And the probability it will get chosen given the fact that it's possible um, is proportional to 1 over like the area of this hemisphere, um, of this whole hemisphere thing. Um, and the expected area of that whole hemisphere thing is going to be, we do the same thing, we do the exact same calculation, but without including the dot product between this and that. Um, so bringing this back to here, um, hold on. This is a preview of what something is going to look like in a second. Um, so we take the integral over all possible points for A. So let's call that set A, but like this. Um, that's the set of all possible points for A. So we integrate over all possible points for A. Um, and for each point in A, um, we take the value of that point, um, which is just going to be the dot product of that point and um, our true moral weights vector. Um, so that's the value of that point times um, probability that point gets included um, in each of the hemispheres. Um, so we do all of that divided by this again, but without this value thing. This might look familiar if you've done other um, statistics stuff with integrals. Um, and that's because it has a lot of similarities with that. Now, just to expand this calculation, what we're going to be doing is we're going to integrate not over all A, not over all points A, but instead over all angles A. We're, we're going to do basically a double integral. Um, what we're going to do is we're going to integrate over all um, angles away from V A could be. And then we're going to integrate over all A that's in that angle away from V. Um, so that's how we'll integrate A. Let me just make sure I'm getting this right. Or now, first, just to visually show what that means, we can finally bring in this thing from earlier. Um, so we integrate over all of these red segments. We figure out what our formula is going to be equal to, what the value of our formula will result in if we're calculating it for this segment, plus the value 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 for, and so on, for all of these segments. So we're going to integrate for each of these segments from an angle of 0 to an angle of pi away from v. So integrate over all s from 0, oh wait, I'll change the color, from 0 to, oh wait, that looked weird, from 0 to pi. And let me just remind myself what this is going to look like. Um, this is just for me. You don't have to understand what I'm showing you yet. Yeah, okay. So then, um, basically, so we're integrating over all s and we're getting the value of that thing from earlier based on that, sorry, um, okay, so the expected value of that dot product times the probability that we end up with that. Okay, so, well, yeah, we have this for all a with, so we're integrating overall s, and what that really means is we're integrating overall of the angles between, um, a, sorry, over all the angles between our point A and our true moral weights vector V. So first let's put in d theta, meaning we're integrating over all angles like that. Essentially, our double integral is just, if you've taken multivariable calculus, it's just we're integrating over all of the angles of A on this circle, um, and then the angles of A on this circle. Um, and then we're multiplying that by the amount of. Never mind. This analogy is only. You're only on. Okay. Ignore this sentence. Ignore the sentence I just said. Um. So we take this integral, um, given theta, uh, for all. Okay. So the probability that a point A on, like, let's say a 50-degree angle. Here's what we're gonna do. We're gonna do this. Um, the probability that some point A that's on a 50-degree angle from, or no, a 45-degree angle, or no, let's start off with a 90-degree angle away from our moral weights vector. The probability that that ends up in the first hemisphere is 50%. And here's why. It's because um, this point here is within this hemisphere only if, so if and only if the dot product between this point here and this point here is positive. Similarly, th um, so, you know, so when this point is in this hemisphere, this point will also have a positive dot product with this point, meaning this point will be in. Oh, I see now why this other hemisphere was needed. Okay, so, hmm, all right, I see something now, but we'll ignore that for now. So let's imagine we have this, you know what? Let's pretend we only give one sample, and um, let's pretend we only have the sample data of this purple option. One thing I will tell you, one thing that I know is the probability that um, our point A, which is now also our point U, just because that's useful, um, U doesn't mean anything now. Or, sorry, instead of using A, we are now using U. This is just a change in terminology, nothing else changes. We are also now pretending that we only give RAI the purple option as our sample option. The probability that U slash A ends up in Q's hemisphere, given that it's at a 90-degree angle from our true moral weights vector, is equal to the probability that Q ends up in U's hemisphere. Because if Q is in U's hemisphere, then U is in Q's hemisphere. And you know why? Because Q is in U's hemisphere when the dot product between Q and U is positive, and U is in Q's hemisphere when the dot product between Q and U is positive. See, they're both in each other's hemisphere, now they're both not in each other's hemisphere. Now they're both in each other's hemisphere, now they're both not in each other's hemisphere. They both have a positive dot product, now they both don't have a positive dot product. Now they both have a positive dot product, now they both don't have a positive dot product. So the probability that U ends up in Q's hemisphere is equal to the probability that Q ends up in U's hemisphere, given that 90 degrees. What is the probability that Q ends up in U's hemisphere in this case? Well, it's equal to the probability it ends up in this segment, anywhere here. Now, if we move U to instead be at a 135-degree angle away from our true moral weights vector, then for Q to be, uh, remember, Q has to be in this hemisphere. What's the probability that Q, given that Q is in this hemisphere, is also in this hemisphere? Well, it's 1 in 4. Um, there's a 1 in 4 chance it ends up here in this area, 1 in 4 chance it ends up here in this area, 1 in 4 chance it ends up here in this area, and 1 in 4 chance it ends up in this area. Similarly, if we move A to be pi minus 1/8 of pi, Q only has this tiny sliver to be in, which is 1/8 of this whole segment, so there's a 1 in 8 chance. So that probability, so this angle is theta. Oh wait, no. Another thing to explain is the probability that um, U is in one hemisphere equals the probability U ends up in two hemispheres equals the probability U ends up in the first hemisphere times the probability it ends up in the second hemisphere. So what's the probability it ends up in the first hemisphere? Well, in this case where this angle is 1/8, it's going to be 1/8. In the case where this angle is 1/2 of pi, like this, then our probability is going to be 1/2. If U is exactly at our perfect moral weights, then it's going to be 1. So what is that formula going to be? It's going to be um, pi minus theta over pi. It's going to be linear. It's going to be here. If our point is here, then theta is 0, so the probability is going to be 1. Here, theta is pi over 2, and our probability is going to be 1/2. Here, our theta is pi, and our probability is 0. Um, and if we, so 1, 1/2, 0. 1, 0.75, 1/2, 0.250. Um, that's just what the mapping looks like. So we can replace this. Oh, wait, no, not that. We can replace this probability thing with this. Um, let's just drag that over. Well, actually, no, not. Yeah, this is a better formula that explains it better. Basically, we just standardize theta by dividing it by pi, and then we do 1 minus that. So theta is pi, we get this thing is 0, 1 minus 0, we get 1. Or, sorry, no, yeah. No, this thing is pi, this becomes 1, 1 minus 1 is 0. So pi angle away, we get a probability of 0. Um, and n, as in next, is the number of sample decisions we got. So this time, so if n was 1, this would be our probability. If n was 2, we would do this times this is the probability that it ends up in the first hemisphere. This is the probability that it ends up in 2 hemispheres. Um, it's just the same probability over again. For 3 hemispheres, we would do it times itself again. So basically, we just take it to the power of n. Um, so that is the probability thing. And we can also, and this thing is pretty simple. It's just, you know, the dot product between um, our point A slash our point U and our number of bunnies is going to be um, just a simple cosine. Let me double check. Yeah, is it's just cosine of theta. Um, if you watched Three Blue and Brown's um, dot products video, it's pretty obvious as to why. Hold on, let's move all of this real quick. Bit to the side. Um, so we have this. This is our integral. This is we're integrating over all of a given theta. Um, and um, or rather, and what this means of integrating over all of a given theta is we're integrating over all, like, this is our theta. Our theta is, like, locked in as, like, this is our set of values for a. Given that this is our set of values for a, we're integrating over all of a in this area. Um, or rather, we're integrating some function. We're applying some function to all of a in this area, and we're taking the integral of that. Um, we just said what the function is, and that function is the same for all a in this area, because the function is completely determined by the angle between a and this vector. That angle is the same for all points in this segment. So, um, basically, we're integrating some constant, like the integral of 0.5 from 0 to 2 is just the rectangle of, if you're integrating over um, this segment from 0 to 2, and it has a height of 0.5, then it's just the area of this rectangle. Similarly, if you're integrating over a three-dimensional, um, if you're integrating over 3 dimensions with this, um, hold on. What the heck? The heck is this? What's going on here? This is new to me. Okay. Well, given this three-dimensional thing where you're integrating, or actually no, what's easier to see is given this three-dimensional rectangle where you're integrating over the same area, it's just going to be the area of that rectangle. Or rather, it's going to be, sorry, the volume of that area, the volume of that rectangle. Or in other words, the calculation you do is it's the area of your set of values, um, which is this rectangle, or in our case, S, times the value for each point in that set of values, which here is 0.5. Similarly, for here, for our thing S, it's going to be this value of all that. Um, Ignore the double integral thing. So it's this times this is our 0.5. Now we just need to figure out our area of our rectangle. But instead of a rectangle, we have this super messy thing here. Now, you don't need to know exactly what the area of this is. All you need to know is what the area is that the area of this circle is proportional to its radius. Um, And how do we define, so how do we find the radius? Well, simple. It's, you know how this is cosine of that angle? It's just going to be the sine of that angle. So, um, let's get ourselves, where's our sine of that angle? It's some constant times the sine of that angle. Um, Hold on, let's move over that. Um, Whoopsies. Yeah, it's fine that you saw that. Um, so it's some constant times sine of that angle. Um, and that constant depends on m, so it's some function c dependent on m. Um, I can't move it. Here we go, now I can move it. I keep having to move this d of theta as our equation gets bigger, times some constant. Now, really, it's not sine of theta. It's not really just purely proportional to that. If we upgraded to 4 dimensions, all of this logic would apply, but instead of this being just a circle from an overhead view, it would be a sphere. So the area slash volume of that would be proportional to the radius squared, because, you know, sorry, not a sphere, a circle. It would be like, this is like we would be, we go from, okay, if we were doing this with 4 dimensions, if we added into this number of dogs, number of cats, number of bunnies, if we added number of chickens, then this, instead of being a nice tidy red circle, would be a 3D sphere, and we would get the surface area of that sphere. Um, and that would be proportional to the radius squared. Um, because, if you double the radius of a sphere, you double the area of its surface area. Oh, sorry, you multiply its surface area by 4. And if we did this with a hypersphere, it would be proportional to um, the radius cubed, and so on and so on. Um, a hypersphere would be the radius to the power of 4, and so on and so on and so on. So going back to our formula here, it's sine of theta to the power of m minus 2, because for 3 we know whatever that thing we're raising it to the power of is going to be 1. Um, for 4, when m is 4, when we care about 4 different things, we're going to be raising it to the power of 2. For when we care about 5 different things, it's going to be to the power of 3. So m minus 2. So it's all of this. I'm just moving some stuff around. Divided by, as mentioned earlier, all of this just without that weight from earlier. Now what you'll notice is C of m is some constant, so we can just move it on the outside of our integral. And we can do that for this one too. And then, we can just cancel this out. Um, and now we have our formula that given n and given m, um, this is the formula for the expected value of the dot product between what our AI chooses as moral weights randomly, and what the true moral weights actually are. Um, this is that dot product. Now, this dot product times that thing that is completely determined by O, that we talked about earlier, the expected value of the best option, the dot product between the best option and what our AI thinks the moral weights of the world are, gives you the full formula given N, M, and O. Um, so now there you have it. That fully answers the question from this video. Now the rest of this video is going to be some additional useful commentary. This integral, turns out, is pretty hard to simplify. Oh, and also we can now ignore this s. This is just the formula. This is also the same formula as this formula here. Um, it's just tidier. It's just nicer, it's cleaner, and I like this one better. But the constants cancel out, so it's convenient. Um, Now, give me just a moment to set something up here. Oh yeah, apparently, um, I found out that, with a lot of math, apparently a while ago I found out that this, though I think you switch the N and the M, or I think I previously switched the N and the M, um, can be simplified to this formula here. Um, but just in case I was wrong, or just in case I messed something up or whatever, I'm just gonna move this stuff around. In this case, A is theta, and okay, so m minus 2. Wait, is that right? No, that gets raised to the power of n. Whoops. Okay. So this is that integral from earlier. And that's a bit laggy. It's really laggy. Wow. And what you're looking at here is we're taking y as the n input and x as the m input. Remember, n is the number of dimensions. And as that gets closer and closer to infinity, we get more and more accurate to the real world. Because the real world has an infinite number of things to care about. Um, and an infinite number of problems. It's easy to model the world in terms of how, like, one easy way of modeling the world in terms of some vector calculation, by the way, is how solved is this problem times how important is this problem. Um, like, how solved is the problem of poverty times um and 0 being not solved at all, one, or sorry, 0 being fully solved, 1 being not solved at all, times how important is poverty. It affects however many people. If you manage to get it from 1 to 0, you've completely solved poverty. Um, that kind of thing. Oh my gosh, this is still loading. I can't move around, or I can't rotate. Oh, here we go. Did I get this right? Am I getting this right? Whoa, that looks weird. Um, yeah, okay, so, um, what I did is I multiplied this whole thing by 500, and like, let's set this graph to be 1. Ah! Mistake. And now it has to load again. Okay, so now this is 1. This plane shows, um, a value of 500. Only values of this which are larger than 500 will, when multiplied by 500, have a value larger than 500 and thus will show up. So only when this is larger than 1 will something show up on our graph. Now let's set that back to A, and let's put A at 0.5. Now this shows the set of scenarios where, like, a point with, say, a y of 400 and an x of 200, which means an n as in next, of 400, and an m as in monster, of 200. Um, when we calculate that for those two values of n and m, it will turn out to be larger than 0.5 because if it's larger than 0.5, then when multiplied by 500, it will be larger than a times 500. So every point here represents a place where this formula goes, where that dot product mentioned earlier, um, is larger than 1. So if there's 400 different things we care. I flipped around the N and the M somewhere here, I'm sure of it. Um, I am sure of it. Um, hmm. Am I getting this right? The N is the number of things we care. No, I'm getting this right. So essentially, um, what this tells us loosely is that if you double the number of things you care about, if you double X, then you double the amount of samples you need to get in order to meet some level of accuracy. Say 0.5. You know, if you want your AI to, if you want your AI's moral weights to, on average, be about 50% off from the world's true moral weights, given all those assumptions, then you're going to need to, like, hmm, let's see, is that, like, if this, like, let's say this is at coordinates 10x, 20y. Then if you double x, meaning you now care about 20 things instead of 10 things, you need to double y. You now need to give your AI 40 samples to be half as accurate to reality. Um, and just to give you a sense of what that is for higher levels of accuracy, like for to be really accurate, if you care about 10 things, then you might need to sample like 1,000 different decisions in order to get, or maybe, no, maybe you only need to, if you care about 10 different things, then maybe you need to sample 100 different. Actually, no, yeah, let's figure out what the exact value is. Let's say you want your A to be 0.9, meaning you want to be within 10% of the actual moral weights of the world. You know what? I can just type in 0.9. Um, and let's say you care about 100 different things. X is 100. What Y do you need to be at? Let's see. Um, X 100 is there. Oh, wait, no, now I can't see it. Ah, home. Um, and then zoom back out. Wait for it to calculate everything. I'll just wait for that to load. And as I wait for that to load, I'll explain something else. Theoretically, what you could do is you could give the AI any distribution of possible moral weights. Not just it has, um, like essentially what you're, um, oh, it's loaded. Okay. So it seems like, um, for an accuracy of 10% within the true moral weights of the world, um, if you care about 100 things to start with, it seems like you're going to need to give about, that looks like, I want to say 1,000 samples, but let's see, maybe 500? I'm not sure. You can figure out the exact angle. Um, anyways, some more final thoughts are that, like here, what we did is we said everything in this segment, um, everything in this segment of Q has a 100% chance of being possible. Everything here, 0% chance of being possible, because we know for sure that the right decision was Q. What you could theoretically do is run these numbers again and say we think there's a 99% that decision Q was correct. So everything here is weighted 0.99, everything here is weighted 0.11. And let's say we thought there's a 60% chance U is correct. So everything here we multiplied by 0.6, everything here we multiplied by 0.4. So we weigh everything in this section by 0.01 times 0.4, everything in this section by 0.01 times 0.6, everything in this section by 0.99 times 0.6, and everything in this section by 0.99 times 0.4. Figure out what the average vector is, um, scale that up to have a weight of 1, and find the dot product between that and our true moral weights vector. And you could figure out the math of the expected dot product there if you take however many different decisions, however many different hemispheres, with some distribution of how confident you'll be, in order to more accurately figure out things in the real world, where we'll say, "Oh, we're not sure if this is a good decision, but we think there's a 99% chance this is a good decision." You could do that if you wanted to. Another thing you could do if you wanted to is still assume that 1010 thing and see, what's the average point on this whole section? In other words, instead of taking a random moral weight, a random point out of the set of possible points, which is anywhere in this section here, you take the average point. And the average point here would be here. If you picked a random point, there's a good chance you'll get something here, or here, or here. But this seems way more accurate. And let's see what it looks like for a different U and a different Q. Um, and fun fact is when there's just 2 points, the average is just gonna be the midpoint of the two, but scaled up. So let me find that real quick. Here's the mid button. Yeah, midpoint or center between Q and U. Um, and then let's see. Want to give D like a okay, I guess I'm gonna have to do this the hard way. Give me a second. Okay, so the distance between G and that point at the top, like, look how much closer G is to the center than, like, some random point on these two hemispheres, like some point here. It gets way more accurate when you do that. But the math is way harder to figure out a formula for how close it is. So you could try that and you could try to get AI to do that. But AI couldn't even figure out the first formula. That took me like months. Um, so like you might have to be like, I don't know, a few years from AGI or a few months from AGI before you can calculate that formula to get a slightly more accurate conclusion and takeaway and make slightly more accurate decisions. It doesn't seem worth it. It doesn't seem worth the time investment. That time could be better used calling Congress to get them to not make something like this. Um, and by the way, I really do not endorse fully using this model of morals for your AI. You could maybe use this model of morals for your AI and have another plain AI, like just I don't know, Claude Opus 4.6, review each decision that that your much stronger AI chooses to make, and say, do I think this is a good decision or a bad decision? Like if your much smarter AGI says, I think it would be a good decision to release this virus into the world for the betterment of the economy, blah blah blah. Then you figure out some way of automatically getting all of the thoughts of your incredibly smart AGI, and all of the reports and all the research it did, distill it into a report for just Claude Opus 4.6 and say, hey, I'm thinking of making this decision. Here's a report on my decision. Um, Claude Opus will read the report and say, oh, huh, you did all this research on um, bioweapons and are planning to make a bioweapon to better the economy. That seems like a bad decision. No, I'm not going to let you do that. Claude Opus 4.6 says it's a good checksum. You at the very least need that. Um, but you could do way better. Anyways, that is this video. Um, really congratulations if you made it to the end. This is super impressive if you did. Um, thanks for watching. Um, and look up Pause AI to get started on doing stuff on all of this. Okay.